Hello and welcome to AI4. Our next session will be led by Andrej Malovic. He is the Engineering Manager, Technical Lead at Facebook. Please join me in welcoming him to the virtual stage. All right, take it away.
Okay, hi everyone. My name is Andrej Malovic, and I'm a tech lead engineer manager at Facebook AI, working on personalization. Today, I'm going to talk about recommender systems at scale, and we'll cover some topics that are usually not receiving enough attention when you build recommender systems. To start, let's set up some context why we care about personalization technology at Facebook and why it's so important for Facebook mission. At Facebook, our mission is to bring the world closer together, and our platform has a kind of family of apps and services used by over 2 billion of people across all over the globe. If you look at the way we use personalization, we personalize our experience across many applications at Facebook. And just to call out a few, like one of them is going to be Newsfeed and Instagram, where we're trying to connect people with a meaningful posts that they likely to care about. We surface in the groups that you might be interested and that may connect you to meaningful communities to you. Or in case of Marketplace, we might be kind of connecting you to the items that might be useful for you. In this talk, I'm not going to be doing deep dive in any of these systems in details, since all of them have quite a lot of unique characteristics and challenges, many of which are internal. Instead of this, I'm going to look into common challenges and questions that appear when those recommendation systems are built and point out the areas that are not receiving enough attention. So today's agenda is going to look the following way. We start with talking about overall system design. Then I'm going to talk about retrieval models in details and why we care about this. Then I'm going to talk about ranking models. And in the end, I'm going to talk what could be beyond this. And to start, let's take a look at what is the recommender system and like take a look at generic recommendation system. First, let's start with some basic query flow that happen in system in the details. Given a query, so recommender system is given a query and with user context and information, we want to return list of recommended items that will need to be presented to the users. This list of ranked items is expected to be relevant for a given user and represent things that they care about. For example, in case of newsfeed, it's going to be interesting posts, or it might be interesting groups, might be relevant products, and so on. When we operate in this system, we usually rely on two pieces of information. One of the pieces is item store, which is a repository of items that are eligible to be recommended for a given user. And feature store is a repository of features that we can use to rank those items. Both feature and item store are expected to be operate and scale with a low latency. So if we look a bit closer into the system design, and let's see also how we handle all these challenges at Facebook. First, the thing that triggers this recommender system is going to be a user interaction that will send a query to the system. In case of newsfeed, in case of the newsfeed, this will be the queries that will be asking to show you relevant posts. The query will have all information that is needed by the recommender system to produce ranked items, including both user identifier as well as some of the context information. For example, what is the time of the day, what device user is using, and so on. In case of large-scale recommender systems, there is a list of items that is available, could be really huge. And in many cases, this list could be in millions of items or even more, which is not feasible to rank all of them in a reasonable amount of time. Moreover, most of them are never even seen by a user. To address this part of the issues, there's usually a separate part of the system that is called retrieval. Retrieval, or as we usually refer to it, retrieval stage, which is expected to be fast and frequently, which is expected to be fast and kind of extract items that are relevant for user within kind of from the large list of items. I'm going to talk about this part later in more details during the talk. The next stage of the pipeline is a ranking model, and this step usually relies on some sophisticated ML model that is good at predicting probabilities of different events to happen. For example, it might predict clicks, likes, video views. This step usually needs a lot of information about user and item, which is represented as features stored in feature store. Since the number of the candidates is relatively small, and usually kind of in scale of thousands, we can afford spending lots of time and CPU on spending each of the ranking candidates. And the last part of the recommender system is usually going to be business logic that is focused on things like pruning, integrity, diversification. For example, we might remove some of the items from showing to user purely because we know that the user will explicitly don't like those items. And after we have ranked all of these items, we need to log this information back to the system, so later we can produce even better recommendations and account for the user feedback. It's important to make sure that the training data that we are logging is going to be good, since ML models can be only as good as their training data. And finally, all of this should be done in a really timely manner. And no matter how complex your model is, you have to finish everything within 1 second or even less. So now let's do our deep dive in one of the areas, which is retrieval. So first of all, why do we need this stage? The challenge is that in real world large-scale recommender system, there's a huge amount of possible candidates that could be shown to the user, and this pool usually consists of millions or even billions of candidates. During this step, our primary focus is not on producing the most precise prediction, but rather we want to focus on recall and find the list of items that would be useful for the later stage models in a limited amount of time. Usually it's within 100 milliseconds. There's various solutions that exist for this problem. As an example, like there are classical solutions like collaborative filtering, two-tower neural networks that will be using KNN service, extreme multi-class classification, or deep retrieval that directly optimizes list of items to show. So let's, to understand kind of one of the possible ways how to implement it, let's take a closer look into one of the frequently used approaches for this problem, which is two-tower neural network-based model. To understand the idea behind this model, let's first refresh ideas behind the embeddings. Embedding is a mapping from the original feature space into a low dimensionality vector that captures latent structure of the target domain. Embedding is actively used in various domains, especially in ML and NLP, and one of the most basic embedding models that one can see is a word-to-vec model that represents all English words in the metric space. So as a result, nice property of this representation that items with a similar semantic will end up being represented close in that metric space. So for example, if one take a look at classical word-to-vec models and pick a word Christmas and holiday, those two words will be nearby in the space, while words Christmas and sandwich are likely going to be pretty far apart since the meaning is pretty different. Two-tower neural network is one of the approaches to leverage this property and build efficient mapping from original kind of query user object from original query and object pairs in this space. Like to do so, we can train a neural network that will have two parts of the sub-architecture. One is focused on the query part, and one is focused on user part, that will project in embeddings into the same space and optimize for similarity. For example, cosine similarity. After we have trained this model, there are various ways to leverage it, and one of the most simplest and most common ways to do so is leverage KNN service that will find items that are similar to user query. There are various efficient implementations of this KNN service, since this is a very well-known problem, and there's plenty of open source libraries that will allow you to do so. One of such example of a library is Sparse that is implemented by Facebook AI Research. If one is using this library, it's pretty easy to implement effective search for hundreds or even thousands of candidate items. This next part, I want to cover kind of a little bit more around common pitfalls, things that are usually not accounted when you build in this stage. So even though overall idea of retrieval multi-hashes to our neural network is not extremely complicated, there are various considerations that needs to be taken into account to make it work. For this part, let's kind of take a close look at some of the pitfalls. So one of the issues that you might frequently see is that when you design in multi-stage ranking systems, you might not account for distribution properties of the systems and potential issues from the closed loop between earlier stage model and a later stage model. So as an example, the distribution data that you might see at the retrieval stage and the distribution data that you'll see later on the ranking stage, they are going to be different. The reason for this is because retrieval stage is usually seeing the whole set of items, while the ranking stage will see only the items that are already filtered by retrieval stage. As a result, only if one is using only a set of items that are used, that have been explicitly interacted by user to optimize the retrieval stage, it might produce not optimal outcome because this is not the data set, or this is not the space over which you're optimizing. And second issue that you might see beyond not having optimal data set for training this retrieval model is possible inconsistency between two of your stages. So as an example, even if when your retrieval stage is producing best possible results that could be shown to user, but your later stage model is not able to rank them properly for whatever reason, your model performance will be suboptimal. So in case of your ideal system, you want to be optimizing for set of items that could be ranked by a later stage, and your overall performance is going to be bounded by the later stage. So whenever you're designing a retrieval model, try to optimize it to be consistent with your later stage and not just be optimal by itself. The next pitfall might be coming from overall system design, because in real world there's limited amount of CPU and latency bandwidth available for the recommended system. So allocating too few or time to each of the stages can lead to suboptimal performance and issues. Similarly, there's also trade-offs between staleness of index and amount of time you spend on optimizing it. And so as a result, you want usually to try to focus to optimize the system as a whole, not as independent pieces. And last but not the least, always keep in mind explore versus exploit trade-off, since for the new items, if you're highly optimizing for system, it might, for real purposes, it might be harder to show the items that is outside of user interest, and they will never see potentially relevant things for them. Now let's switch to the next part, which is ranking models. So let's talk about ranking model. As we all know, kind of quality of your model is highly dependent on quality of your data that you feed into your model. So it's important what kind of data you could potentially use inside of your model and either use it efficiently. Most commonly used types of data could be looked into a few categories. The first category is going to be numerical or continuous features. And those features are usually represent various continuous values or counts. And closeness in the space, kind of in the space of these features, usually means similarity of their semantic. So as an example of such features, one can think of user age or time of a day, maybe number of posts interacted within the last 30 days, or number of videos watched within last week, or even various content embedding features, for example, image embeddings or text embeddings that the user might want to see. Second category is usually referred to as categorical features, and those features represent pick one of a few multiple options. Closeness in this space doesn't really mean closeness in the semantics, and a few of those features could include gender, language, maybe device type. And the third type of the features is the sparse features that have some high dimensional categorical features with a small number of categories or IDs, category IDs present. Examples of such features could include post ID, last and viewed videos, or user interest topics. Sparse features are extremely powerful, and if they can be utilized well in the model, since they allow to capture highly personalized signals about user. So for example, if you'll see the difference, there is a big difference in the representation. One of them is male, age 26 to 32 using iOS, versus the same information about user traits, but also showing that this person is interested in machine learning, guitar, and snowboarding. Second representation allowing us, that has the sparse features, allowing us provide much more personalized experience. So now let's talk a bit about how can we handle those different types of features. And either we even able to leverage them well. So for example, kind of one of the issues that one might see is if the feature has really small coverage or really large cardinality in case of sparse features, you might not be able to leverage it well purely because you have too few samples to learn something about the feature. For example, if you use post ID based features, it likely will not work only if you have a few 100,000 of examples, but might be extremely important for larger data sets. Second question that might be good to answer is my model leveraging the features well. To answer this question, we need to talk about possible ways to leverage these features. In this case, I'm going to look into how we can use those features in neural nets. So overall, training neural nets is hard, and which can be limiting factor for wide adoption of neural nets in your recommendation system. And also neural nets are pretty sensitive to the distribution of their inputs and their regionalization. So for example, if you will have two different features, one of them in order of -1 to 1, and another feature is from 0 to 1 million, neural net will have really hard time learning to utilize those features well. So what it means in case of dense features, we usually want to normalize them to make sure that all features are close to normal distribution, which makes them comparable and makes them easy to learn. For case of categorical features, we can apply one hot encoding trick to convert them into a dense tensor. For example, if there's only 3 device types, such as Android, iOS, and web, we can convert them to values 0, 1, and 2, and then represent them as a vector of 1, 0, 0, 0, 1, 0, or 1, 0, 0, or 0, 0, 0, 1. And we can concatenate those features with the float features and feed them to neural net. And last but not the least is sparse features. Same approaches as we used for the previous types will not work because the IDs could be really large in range. But luckily we can leverage embedding tables to convert those features into low dimensionality vector space, for example, 64 floats per ID. If feature has multiple IDs, we can also aggregate those together through kind of pooling techniques. and still produce the same list of floats as per feature vector. It's also important to be aware that initialization of this table might be dependent on number of IDs per feature, since the result might end up being potentially in scale compared to the dense features. Now let's talk about how we can fit everything together. And all the signals could be potentially trained as a single neural network that is receiving kind of both dense and sparse features together. And in case of dense features, we can dense and categorical features, we can feed them through NLP, MLP, and learn interaction properties among the dense features. In case of sparse features, we can feed them through embedding table and kind of get again those float features. The next part, which is usually pretty important, is how to do interaction between dense and sparse features. There are various ways how it could be possibly done, including doing simple concatenation or pairwise dot products, and various more interesting kind of concatenations, various interesting interactions. After this, we'll get another vector float, and we can feed it into MLP to produce final prediction. This architecture is already open sourced as Facebook as part of deep learning recommendation models, or DLRM, and has an example with Kaggle dataset, and that outperforms with kind of winner of this competition. Few important things about these models: MLPs are going to be compute bound, while embedding tables are going to be memory bound. And in case of real production models, can take tens or even hundreds of gigabytes. Which usually means that these models can be trained without model parallelism, and which splits training across different trainers, and it's kind of hard to feed it on CPU and GPU. I'm not going to be talking into complexities of this solution, since it's completely. I'm not going to be doing deep dive into how to train, since it's a completely different topic and will take more time. And the last part, I would like to talk about some limitations of the current system. First of all, whenever you design an recommendation systems at scale, you always want to ask questions, why and what are the limitations. As an example, one of the problems that we know about the current models, they have issues with determining causation versus correlation. And in many cases, if you look at whatever happening in the current world, our model is only able to see that certain events have happened, but not necessarily why they have happened. For example, in case of current pandemic, our models kind of like there are two events that happen together. One of them, there's pandemic. Second one, people are working from home. But if one will be trying to do causation, they can potentially make incorrect one, whereas they'll consider that working from home causes pandemic, which is not the same as pandemic have actually caused working from home. But when models only sees two events together, it cannot really distinguish. Second thing is data and users are not static and evolving over time, and means our models need to adapt frequently to understand the differences. As an example, in case of COVID, people have changed the way they engage with the system compared to what we had seen 1 year ago. As next item is models are complex, and our users are complex and have different interests, such as activities, music, different political affiliations, and many of these activities are hard to represent as a single vector, and embedding vector, and as a result, it might be limiting models. And last but not the least, our models are heavily reliant on feature engineering, and that could be limiting around like source of information that we are able to capture, because humans are good in describing things that are understandable by humans, but they might be not the best for the model. As an example, in case of computer vision before 2012, models were heavily reliant on SIFT and other features. And after this, after convolutional neural nets, people stopped relying on this. And to conclude this part, I want to propose one of the possible solutions that could be used, which is graph learning. And this is like really hot topic in academia. And that's receiving lots of traction. And the nice benefit about graph learning, it allows us to incorporate all information into a single source and look at this and to kind of one end-to-end model that is able to train things without relying on feature engineering. And in case of ranking model, it allows us to get closer to the signals and potentially extract more meaningful features for the final task prediction and learn things better than what humans are able to produce. And yep. And with this in mind, I would like to show you some summary. Whenever designing your ranking recommendation systems, please design things with the problem space in mind. Always keep in mind the bottlenecks and optimize system as a whole. Use the most granular signals whenever you're able to can, and understand how your models, how models work, and also be aware of the limitations of the technology you use. And with this in mind, thanks for your time and your attention. I hope you enjoyed this talk and learned something new from it. And as I mentioned in the beginning, I'm Andrei Malevich, tech lead and personalization tech lead and engineer manager working at Facebook AI. And yeah, thank you for your attention.
Thank you so much, Andre. A big virtual round of applause for you and that incredibly insightful presentation. All right, if you are looking for your next session, you can go ahead and check out the program page or take some time to do some virtual networking and start some conversations with your peers. Thank you so much, and we'll see you around.